we are definitely going to continue with our subtopic we were looking at yesterday, known as chemical energetics or definitely energy changes. Now, when you recall very well, yesterday we looked at some of the terms related to chemical energetics. And just to mention a few out of those we discussed, I am able to do a recap on just one out of whatever we mentioned. I understand you are able to remember, but I'm interested in this term, endothermic. Why am I interested in this term, endothermic reaction? Because this term is going to actually link us to our term we are going to start with today. I divided the suffix from the prefix of this term, endothermic. The prefix here, endo, is having en. This en, which can be concluded to come from the word enter. Therefore, we concluded that the prefix endo means to enter. Now, what is entering? We are having this suffix thermic, which comes from the word thermo, and thermo means heat. Now, from here we are going to conclude that we have heat entering. Now, where is heat going? Heat is going to the reacting system because we are talking about chemical reactions. And when a chemical reaction is taking place, actually it is going to be taking place in a container. So that container is what we call a reacting system. A reacting system is actually the place or region where the chemical reaction is taking place. Understand that. That's a recap. And we gave examples of endothermic reactions such as the process of photosynthesis, the process of photography. Those are reactions. We also gave some of the processes such as dissolving ammonium nitrate in water, that is endothermic. Or maybe melting ice, for example, that is endothermic because we are going to allow heat to enter the system. Now, from there, we are going to continue with the terms related to chemical energetics, the terms we are going to be meeting. We are going to start from the opposite of endothermic. The opposite of endothermic today is nothing else but exothermic reactions. So we are saying where we are going, we are likely to meet this term, exothermic reaction. When we meet exothermic reaction, what are we going to be understanding? So I am going to write this word here, exo, and then we have thermic. Exo is having this EX, which can be completed to be exit. Now, exit talks about the point at which something is going out. So when we say exo, it means something is going out. So exo is coming from exit, where we are saying here, since we understand thermic is coming from thermal, we are talking about heat is coming out of the reacting system. And where is that heat going to go? It is going to go to the nearby surrounding, the area which is surrounding the reacting system. For example, if I have a container, in this container, the chemical reaction is taking place, and if that reaction which is taking place in the beaker is exothermic, I expect heat to be going to the surrounding areas, the area which is surrounding my, the area which is surrounding my beaker. So this is just the nearby surrounding, and this is this area or the surrounding which is going to receive heat. Why? Because the chemical reaction there is releasing heat. That is very important, my dear learners. Very, very important. Now, we have examples of exothermic reactions. We have examples of exothermic reactions. The first one is combustion. The first one is combustion, which is also known as burning. So combustion is actually the burning of a substance. And in that process, the new substance is going to be formed. Provided the new substance is going to be formed, that process qualifies to be called a reaction. And whatever substance, when a substance is able to burn, that substance deserved or qualifies to be called fuel. A fuel is any substance which is able to burn. And when something is burning, the new substance is formed. For example, we have examples of fuel: hydrogen. Hydrogen gas is fuel on its own. We also have solid carbon. This is also fuel. We can also have some hydrocarbons, such as maybe alkenes, all those are fuels. What are we talking about? In the presence of oxygen, because oxygen supports burning, when this fuel hydrogen is burning, we are going to have water vapor being produced. This is the new substance. Here, when we burn any substance containing carbon, we are going to have the new substance carbon dioxide being produced. If this fuel contains, for example, carbon with X number of moles and hydrogen with Y number of moles, we don't know the number of moles, we are just using any hydrocarbon plus oxygen, we are going to have carbon dioxide. Pardon me, here I am supposed to say carbon dioxide plus water. We are having new substances being formed. So combustion is actually an example of chemical reaction, and we are saying this combustion is an example of an exothermic reaction, because in these reactions, heat energy is given out. Meaning, these substances are chemicals, and every chemical substance is going to contain chemical energy, whereby when these substances are burning, that chemical energy is converted to heat energy. That's the same heat energy which is going to be released to the surrounding. That is very important, my dear learners. Very, very important. Another example of Exothermic reactions is nothing else but tissue respiration. Tissue respiration. Now, in tissue respiration, we are having glucose. This glucose is reacting with oxygen. We are having the products which are carbon dioxide, water, and energy. Remember my previous equations where I sampled an hydrocarbon where I said, this time I'm going to use the actual one. For example, I say methane. Methane, this is an hydrocarbon I was representing to be CX, maybe Y, but this was representing any hydrocarbon, but in this case I am being specific. I am going to use methane plus oxygen. Okay, now here I am saying this is respiration, pardon me, this is combustion, and I'm saying this is respiration. In each case, oxygen is involved. Now, what is the difference between tissue respiration and combustion? When you meet that question, because both of them are exothermic reaction, that is the similarity. What is the similarity between an endothermic, or should I say combustion and tissue respiration? In combustion and tissue respiration, in both, heat is given out to the surrounding, and in both, oxygen is involved. Now, what would be the difference? In combustion, fire is involved. Here we are burning the substance. In combustion, fire is involved. Here we are burning methane. In respiration, we are not burning glucose, but we are oxidizing glucose. So, respiration is an oxidizing process where you just add oxygen to glucose, and when you add oxygen to glucose, you are going to produce new substances. No burning is involved. Glucose is not going to be burning, but it is just going to be oxidized. Definitely, we are going to have the similarities in terms of what is going to be given out. Here we are going to have carbon dioxide and water. Even here we are going to have carbon dioxide and water. But on combustion, it is the result of burning the fuel. You need to understand that. Tissue respiration takes place in the living organisms. And that can not qualify to be combustion because we don't burn with a flame. No. But in combustion, we burn with a flame. That is very important, my dear learners, for you to just understand the concepts. This is chemistry. Let us understand when we are learning. We go to C, dissolving sodium hydroxide crystals in water. Dissolving is not a chemical reaction. Dissolving is actually the physical process where we just change the physical state of our reagents. For example, we are saying dissolving sodium hydroxide, the crystals. And when we see this word, the crystal, we are talking about the substance which is in solid state. Now, when we put sodium hydroxide in water, the solvation of sodium hydroxide, the process of forming sodium ion and hydroxide ion in solution, this releases a lot of heat. That qualifies this dissolving of sodium hydroxide to be an exothermic process. Meaning the process of dissolving sodium hydroxide is an exothermic process because heat is evolved to the nearby surrounding from the reacting system. That is very important. Now, take note, exothermic reaction is all about bond forming process. Endothermic, in the previous video we said endothermic is all about bond breaking. Why are we saying endothermic is all about bond breaking? Because when heat is being supplied to the reacting system, that heat is going to be received by the reactants, and in the reactants the bonds that hold the particles together will break. And what is going to cause that is the entry of heat. That heat will break the bonds that holds the reactants together. Now, just imagine now heat is coming out. What was breaking the bonds is now coming out. Now, since what is there to break the bond is coming out, meaning the bonds now will start reforming. We are going to have the products that are going to be forming the bonds because heat is coming out. That's the reason why when you put water in the fridge, water is going to freeze, will be converted to a solid. Why? Because heat is going to be coming out. As the result, the particles will start coming closer to each other, forming the new bonds. Why? Because heat is coming out as you are cooling. Therefore, the exit of heat brings about bond formation. Very, very important. So, when we are reacting, for example, glucose plus oxygen, when the reaction is taking place, we are going to have carbon being dissociated from hydrogen, and hydrogen itself is going to react as an atom. Meaning, this hydrogen from glucose when these substances are reacting, oxygen is going to react with carbon alone, meaning there will be the breaking down of hydrogen from carbon. So meaning we are going to have heat which is going to break down this glucose molecule so that we can have carbon being isolated in such a way that it will react with oxygen. That is bond breaking. Now, for these new bonds to be formed, heat is going to be going out of the system so that oxygen can bond with carbon. Oxygen can also bond with hydrogen to form water. That is very, very important. Characteristics of endothermic reactions. How are you going to know that the chemical reaction is an endothermic reaction? Or how are you going to know that a reaction is an exothermic reaction? So we are saying characteristics of exothermic reactions. Number one, energy is released to the surroundings. How are you going to know? You are going to have a laboratory thermometer. You insert it in the reacting system. If energy is coming out of the system, we expect the temperature of the solution inside here to be increased because the chemical is giving out heat. Therefore, that heat which is coming from the chemicals that are reacting will go to the solution, and that heat is going to actually raise the temperature of the solution. The same temperature which is going to be increased is going to be recorded by the thermometer. So we expect the temperature of the liquid to increase as the thermometer is going to record that. That's the reason why the same heat which is coming out will be going out the reacting system. It will be going out to the surrounding from the reacting system. So we expect the energy to be released to the surrounding. If you touch the container, you are going to sense that hotness of the container because heat is coming out of the reacting system. Point number 2, reactants have more energy than the products. Remember, my dear learners, the formula I gave you in our previous video to calculate the enthalpy change. We said enthalpy change equals the enthalpy of the product minus the enthalpy of the reactants, provided the graph is given to you. You use this formula. Now, this point is saying the reactants have more energy than the products. In this case, we are going to say, since the products who have less energy, for example, 20 kilojoules, and the reactants have more energy, reactants have more energy. So we are going to say, for example, 40 kilojoules, like that. Here we have 20. When you subtract 40 from 20, your answer will be negative 20 kilojoules, meaning the enthalpy change will be negative. Why? Because the energy of the products is actually less than that of the reactants. That's the reason why for exothermic reaction, the enthalpy change is always negative. We are also saying temperature of the reacting system increases. I was talking about this. Another characteristic is that bonds formed are relatively stronger than bond broken. So the bonds that is going to be formed in the products will be greater than the bonds that were broken to form those products. That's the meaning. These are the characteristics of exothermic reactions and exothermic processes. A graphical presentation of exothermic reactions. We call that energy level diagrams or energy level profiles. How are you going to demonstrate an exothermic reaction using a diagram? We have a diagram here. We said, on the characteristics, we said the energy of the reactants will be greater than the energy of the products. So we expect, when we are drawing a graph of an exothermic reaction, the reactants will have more energy. We are increasing energy upward, meaning the energy here leveled with the product is less than energy at this point where we are having reactants. So we can say here we have, for example, 20, here we have 40 kilojoules. Why? Because we have reactants having more energy than products. And in this case, from the graph, we are going to conclude that the delta H, which is enthalpy change, will be negative. Because we are going to subtract the energy of the reactants from the energy of the products, which will be 20 minus 40, for example, and your answer will be negative 20 kilojoules. This indicates the enthalpy change, which will be negative. This sign negative is just indicating that the process is exothermic. It is not defining energy to have a negative. There is no energy with a negative charge. But we include this negative to show that the process or the reaction is exothermic. Understand that. And when you are calculating, it's very important to include the negative. because this negative is the only sign which is going to show the examiner that you calculated your answer and your answer was having a negative, communicating that this process or reaction was an exothermic reaction. So that is our mathematical communication or expression of answers. So, since we have done this, definitely I understand, my dear learners, looking at your intelligence and capabilities, you'll be able to link and show the differences between endothermic and exothermic reactions, giving the differences in terms of characteristics of both exothermic and endothermic processes and reactions. You should be able to give or to show the graphical presentation of both endothermic and exothermic reactions. In future, you are likely to be subjected to a different way of presenting graphs or diagrams of endothermic and exothermic processes or reactions. So allow me to demonstrate one example of a different way of presenting a diagrams for both exothermic and endothermic processes. For endothermic, you may meet a graph like this. Here we have energy. Definitely in kilojoules. And here we have progression of chemical reaction. I understand, you know, you are supposed to write this in full. I am just demonstrating here. Progression of chemical reactions. Now, how are we going to express or present our endothermic process? We understand that in an endothermic process, the products will have more energy than the reactants. So the level of reactants will begin at the lower energy level, and we are going to increase it like that. And the products will be at the higher energy level. So here we are having reactants, and we are having products. And remember how we calculate the enthalpy change, my dear learners. The enthalpy change actually is the difference in energy content between the reactants and the products. So we are going to develop dotted line, and we show the difference, the distance from there to there. This is where we are having enthalpy change. Okay? And if the question is saying you need to indicate the activation energy, remember, my dear learners, activation energy, the minimum energy that must be available or absorbed by the reactants so that the chemical reaction can take place. So the activation energy will develop from the reactants because it's the reactants to gain that minimum energy. So the reactant, the activation energy will come from the level where we are having reactants to where we are having a transition state. A transition state is the point at which the reactant splits and starts to form products. That's the transition state. So this is the activation energy. Very important. So remember to indicate the energy and the progression of a chemical reaction. Indicate the products, indicate the reactants, indicate the enthalpy change. If necessary, indicate the activation energy. If at all they have given you the reactants, this is the point where you are going to write your reactants. For example, carbon dioxide plus water to form glucose plus oxygen. So on the products, we are going to say glucose plus oxygen. On the reactants, we are going to say carbon dioxide plus water. That is very important. That is an example of a different way of presenting an endothermic energy profile diagram. The opposite will be exothermic. Again, under exothermic, we said the products will have less energy than the reactants. So we are going to start from, we understand here we have energy in kilojoules. And we have progression of chemical reaction. Now, since the reactants will have more energy, we expect to start from at maybe this point. We are going to have reactants. Actually, we are going to have activation energy, and then we are going to have products, because products will have less energy. So we are going to say reactants here. And we are going to have products here. Remember, my dear learners, that the enthalpy change is actually the difference in energy content between the reactants and the products. And this is the level where we are going to have products. So this distance between the level of products and the reactants is where we are going to have the enthalpy change. And the activation energy is the distance from the level where we are having the reactants to the transition state. And the transition state is at this point. So here we are going to have our activation energy. Very important. So you need to understand the principles, my dear learners. Take note, I have tried to show this, a different way of presenting the diagrams for both endothermic and exothermic processes and reactions. Thank you so much for understanding. Make sure that you subscribe. Don't forget to do just that, so that we can continue learning chemistry, making it simple and simple, so that at the end of the day you are going to enjoy that paper. I promise that Time will come when I'll start answering past papers. Let us learn and let us continue to pull through. Enjoy the video. Make sure you revise to be wise, otherwise no rise.
Are hot, they're that way because when these react, energy is lost. The opposite is not the same. Then what? The chemicals take energy and the temperature drops.